Okay, let's do that. Again, we have this here. We have a U here. We have an interface here. Okay, so the next, okay, so f of u bar is no longer useful, right? It's no longer useful because we don't want to compute, we only want to evaluate f at the left and right values. So we need to do a reconstruction here, okay? We want to first reconstruct UL at faces. L is so how many ULs do we have? Zeros, n plus 1, 1. So the ULs, we have as many ULs as there are interfaces. Okay, and UL 0 because we don't have anything beyond the goal cell, so we keep UL at the left of the first interface, which is immediately outside the boundary, to be equal to the boundary condition. But now from the second one, we want to do reconstruction. So UL from the second to the end. Okay, you know what? Let's do for r equal to 2 to n plus 1. And UL of I would be equal to U of I think I have a plus of 0.5, half of delta x, and the delta x actually cancels with the over delta x. So 0.5 times U of I minus U of I minus 1, right? So that is our formula here. U of I plus 1L is UI plus, this cancels for uniform grid, and this also cancels for uniform grid. So half of UI minus UI minus 1. All right, is that good? UR is also equal to 0, n plus 1, 1. For I goes from 1 to n. UR of I would be equal to U of I plus 1, right? Is that right? So go from 1 to n. I think that's right. I plus 1. At the same point, we want to take one more value. I get minus 0.5 U of I plus 2 minus U of I plus 1. Right? Did I make any bug in this? That's gonna go outside the bound. Okay. U of n plus 2 I think exists because I put two goal cells on both ends, right? Yeah, thanks for checking that. All right. Now FU interface is equal to this, and now it actually gets easy. So if UL of I is greater than UR of I, FU interface is equal to, not only I need to compute UL and UR, also I need to compute FL is equal to the flux at the left is equal to UL square over 2. That's Burger's equation. And FR is equal to UR square over 2, Burger's equation. Okay, so if U left is greater than UR, FU interface is max of FL FR of I. So it's good everything is I at this point. Now this is R 0, okay. UL, yeah, thank you. FL and FR should also be I, right? And everything else is the same. Okay, it's good. Let's remake our stuff with 128. Here I'm just going to just draw something random. Okay, and x is equal to 129 xx, and I'm going to do a close and close and the for loop. Right. Okay. Cool. So we do see shockwaves going here, and we no longer see this continuity thing that is appearing in the middle. All right. So that's a good sign. We have a second order scheme going on, and it's much better than our first order scheme using the good enough flux. Okay. So that's great. And the key to that is reconstruction from the two different sides of this domain. Yes. Okay. That's weird. All right. So let's start talking about the total variation of a scalar conservation law. So one of the things the scheme I just mentioned doesn't do well is to conserve the total variation of the scheme. So next lecture we are going to reuse what we have just coded up and devise a case that like the scheme does not perform as it is intended to. So let's actually try that. That's not on this one. So let's do a case where we should have a shockwave that stays stationary. Okay, so that is a case that is different from kind of the randomly drawn solution we just had before. Okay, and let's see how the solution would evolve in that case. okay, it actually does pretty well. So okay, so it'll may take some time for me to construct a solution where it doesn't work well. But let's actually, okay, so let's do this. Let's do a little bit different. Let's go away from the Burger's equation, because the Burger's equation is actually quite an interesting thing to do. But let's actually switch from the Burger's equation to a linear advection equation. So what do we do if we want to, which line do we want to change if we want to solve a different equation? Huh? FL and FR. So how should I change it to make it a linear advection equation? Change F equal to U is the flux for the linear advection equation. Now we are solving linear advection equation. All right. So let's the boundary condition I have right now. Oh, not only that, but also this line. We have to get rid of these two lines, because for the linear advection equation, we don't need that anymore. The solution either goes monotonically increase. I mean, F either goes monotonically increase. It's always monotonically increasing. So yeah, we only need to take the max or minimum. Okay, good. And another thing I think I want to change a little bit is the boundary condition, because I want to see how the solution evolves for a longer time. Unlike the Burger's equation, the linear advection equation keeps going towards the right. So if I want to see the solution evolves for a longer time, I want to make a periodic boundary condition. So to do that, my U would be U end, U1. Okay, is that right? That's right. So that makes me periodic. And I think I'm close to done, but let's do something quick. So I'm also drawing this solution here, and let's do it for a little bit further time, 1,000. Yes. Yes. You mean if I do that? Yeah, this is called at every step by OD45. Yeah, that's right. And because I'm drawing such a function here at the two ends, there are also two discontinuities actually. So for I equal to this, okay, now I'm going back to change my for loop to, let's say, 1,000. Okay, let's see how this evolves. Okay, so do you see the function over here, how it looks like? So it's supposed to keep the shape, right? It's supposed to keep like a square wave and keep advecting towards the right, but it creates artificial oscillations. So this is the phenomenon we want to get rid of in the next lecture. And it doesn't appear for Burger's equation. For Burger's equation, because we are evolving for such a short time, and the shock wave actually dissipates everything. But like for linear advection equation, it becomes more clear. We need to do something to fix this. Okay, so I'll see you tomorrow actually to discuss further limiters and how we can construct a total variation diminishing scheme.